So, good afternoon, everybody. I hope you had an enjoyable break. We start right on time because we have an invited guest from abroad. David, I don't even know, are you in the US right now or in Israel?
No, in Israel.
Israel. So, David, of course, originally intended to be here, but he has a newborn baby, Michael, since a few days. So, there are more important things than science, obviously, at some point. So, we're very happy that he joins us now to give his talk online you have worked a lot on the information bottleneck method. You will be presenting also about self-supervised learning. So that is something also, I think, there where we can connect information views and machine learning. So we're looking forward very much to your talk. And I think this time we will take questions after the presentation. I think that makes sense. So please save your questions for after the talk, okay? Okay, Ravid, so the floor is yours.
Thank you so much. Thanks so much. And yeah, I'm sorry that that I'm not in the conference personally. So today I'm going to talk about information and self-supervised learning, and how can we look on self-supervised learning from information theory perspective. Okay. First, I want to say thank you to a lot of great collaborators that basically did most or all the work that I will present today. So let's start. And I don't need to tell you that deep learning is good, right? All of us use it all the time. But we need a better understanding of deep networks, and we don't have a good understanding when they are working and when they are failing, and why they are doing a lot of things that we see now. And I will suggest today that you can look on deep learning from information theory perspective, information theory point of view. And of course, if you are talking about information theory, we must start with Shannon, that said that the best approach for a given problem is to try to restate it in just as many different forms as you can. And again, this is exactly what I will try to do to give you another or different perspective on deep networks. Of course, that we need to not to take it with a grain of salt, because also Shannon also said that most of his decisions are not aligned with a financial value or any value to the world. Right? Today we know that it's not true, but he said it. So let's start with the supervised case, okay? And let's start, what does it mean information in neural networks for the supervised case? So we have our input X, and we have our observed, we have our labels Y, and we want to create a model to learn a representation that will give us predictions about the labels. Okay, so we insert the input X, and we want to get Y from our model, and we want to match between the true Y and the predicted labels. That's it. Very simple. And many years ago, Tali Tishby and others said basically what is the optimal representation in this case. And what is the optimal representation? The optimal representation that you can get from an information perspective is to compress the representation and the information that you have with the input from one hand, and to increase or to keep the information that you have about the labels. Okay, and you have this trade-off, and you have a parameter that controls this trade-off. But this is basically what you want to do: compress your input from one hand and preserve as much as information that you can about the labels from the other. Okay, and this is like a general perspective. It's not related specific to neural networks, but just like you have random variables, and now what is the optimal representation of this random variable? And a few years ago, we applied to neural networks, and we said, okay, we can look on a neural network from information perspective, and we can look for all the layers. We can look for each layer. We can look on the encoder of this layer and the decoder, or how the input process to this layer, and how the layer tries to decode its representation to the prediction. And we can look over all the layers. And what we found, so we try to measure these quantities, okay, these information quantities for each layer. So this is a graph we measured. We took a regular network, okay, without any regularization, and we measure for each layer. We measure the information with the input and the information with the labels. Now, what we found, so here x-axis is the information with the labels, y-axis is the information, x-axis is the information with the input, y-axis is the information with the labels, and what we found that for all the layers, and this was quite surprising at that time, that for all the layers you have two distinctive phases. One, you increase all the layers, increase the information with the labels, okay? And also keep the information with the input. But at the second phase, you have a compression, a really slow compression, that actually the network and all the layers, one after the other, compress its representation, but at the same time, keep the relevant information about the input. Okay, so the different colors here are the different epochs along the training process. So the bottom line is the network, the random network at the beginning of the training, and each path here is a single layer. Okay, so the path that is the most to the left is the output layer, and the path that is really new to the right left corner, to the right upper corner, is the first layer. And you can see here the green line actually distinguish between the compression phase and the fitting phase, the phase that we saw at the beginning. Okay. So this for the supervised case, everything is very easy, because you have labels. You can distinguish what is the important information and what is the irrelevant information, and everything is okay. And there are a lot of works after it that try like to measure different quantities. I don't need to tell you that measuring information empirically, it's very hard, and there are a lot of ways to do it, and a lot of point of views. What does it mean even information in deterministic networks, etc., etc. So many a lot of people try to take it for different directions. Some develop more theory and some more practical things. Apply regularization on the information in the supervised case. But I just wanted to give you a brief introduction, and I want to talk about self-supervised learning and information theory, okay? Or how can we extend this perspective to the self-supervised case? So we have several of papers about it. You can look on them. They are online. So self-supervised learning. We have, what does it mean? In the most general view, we have two inputs, okay? It can be an image and some augmented version of this image. So we have X1 and X2, okay? We transfer these two inputs through two different networks. It can be the same network, it can be different parameters. And then we get two representations, okay? Z1 and Z2. And now we have some distance function that basically want that two inputs, two versions of the same image. I want that they will be close to each other, close to the X1 will be close to X2. And if I have two versions of different images, I want that they will be with some distance from each other. Okay, so I want to make the images, the representations of the images from the same image close to each other, and I want to pull apart the representations from two different images. Okay, this is very general view of self-supervised learning. Okay, we don't have labels. We only use signals that are in our data and some prior knowledge as the augmentations. We assume that we have versions, different versions of the same sample. This is the assumption. Okay. Okay. So how we try to deal with this problem? So first of all, we try to look, we try to understand what does it mean information in deterministic networks, because all these methods, self-supervised methods, are deterministic. Okay, you have an input and you have a deterministic function. Your network is a deterministic function of the input, and you have an output. So what does it mean to talk about information and to talk about probabilities in this case? So what we try to do, so basically we said till recently, most of the works basically assume that you have a stochastic network. They said, let's assume that our network is stochastic. You have some noise in the network, the weights of the network or the representation of the network, and then you have a stochastic output and everything is okay. And we said something differently. We assume that we have some input noise. For example, we have samples that each sample, each example came from a Gaussian, okay, and then our data set is a mixture of Gaussian. But the important thing is that because we have noise in our input, we don't need to assume noise stochastic networks, and we still can analyze the output of this network. Okay. Again, I don't want to get into the details and how we analyze it. You can look on the papers, but this is the general assumption that helps us to analyze how information evolves in the network. Now, the second thing that we wanted to do is to take. So we start. So we start with an objective, with a current objective of self-supervised learning method, and we try to understand what are the different assumptions that we need to assume in order to get some optimization of information. Okay, so what are the assumptions that if we will make these assumptions, our information objective will be an actual objective that other people use. Okay. And now let's try to understand the objective. So the objective, what we want in self-supervised learning, what is the optimal representation, or what is the optimal objective that we can think of? So as I said, in the supervised case, we have labels. So 25 years ago, they gave us the answer that we want to maximize information of the relevant maximize the information of the relevant inputs and minimize or compress the information that it's irrelevant. Now, this is great, but what we are going to do when we don't have labels, what we want from an optimal representation in this case. So one possible solution is to say, okay, I will maximize the information that I have. I have two views. Let's maximize their mutual information, their shared information. And that's it. Let's optimize this one. What is the problem? The problem here is that we don't have any compression, right? And our intuition from the supervised case is that we need some kind of compression in order to learn. For example, you can say, let's make one-to-one mapping, right? If our network is a one-to-one mapping of the input, you will preserve all the information. But of course, that this is not a valid network. This is not what you want to do, and this is not what people are doing in practice. So what we actually want to do here, what we want to optimize, and what representation we want to get. And the answer to this question is much more complicated. There are several answers, and basically they based on your assumptions and the assumptions that you are making along the way. So I will give, for example, one assumption that we can do and how it will affect our objective. So as I said, we want to compress some parts of our presentation, and we want to preserve the other parts of our presentations. And there are a lot of ways to do it. A lot of different measures that each one of them will give us different answers and will bring us to different assumptions. For example, we can look on the multi-view assumption. Okay, so in the multi-view assumption, if we assume that these two views, that we have some labels, okay, we don't know these labels during our training, but we have some downstream task labels. Okay, you are training your self-supervised model without labels, but you know that at the end, there are some labels that they are like the right labels, okay, for the downstream task. And now you assume that the information, the only important information is the information that shared between the views, okay? In other words, you assume that the conditional information given one view, the conditional information of the other view with the labels is very small. And why does it make sense? Because, for example, if you're doing rotation, okay, if you're doing some rotations and your views are now different rotations, so you can assume that the rotation basically doesn't hurt the labels. Your downstream task is invariance to rotation, for example. So it makes sense most of the time. And in this case, we can show that the optimal representation is to keep the relevant information. Okay, what is the relevant information? So the relevant information is Z1 and Z2, but at the same time, to compress the irrelevant information. In this case, the irrelevant information is the information that goes from X1 to Z1 given X2. And why it's irrelevant? Because we know that the only important information, this is our assumption, that our assumption is that the only important information is the shared one. And the information that we don't share between the inputs is irrelevant. Okay, so we can see here that given an assumption about the nature of our data, we have some optimization objective. Okay, and as I started to say, the next thing that we did, so now we have some objective, and we basically try to look what are the assumptions that we need to make in order to get a real objective that other people use it in real or practical networks, practical methods. And what we found basically that most of the current methods have two parts, okay, in their objective, or you can separate these methods to two parts. One is the classifier, okay, how well I can classify one representation based on the other representation. Okay? This will make two points that are similar to each other, that came from the same image, similar to each other, because I want that they will be similar. I want to classify them. And we have also a regularizer that basically prevents from collapsing. It prevents from all the points just to collapse to one point, and that's it. In the supervised case, by the way, it's not happened. You don't need this regularizer because in the supervised case, this entropy is constant because you have the labels. It's the entropy of the labels that it's constant. And of course, that after you identify this, you can try to just plug in different information and entropy estimators. Okay, there are a lot of different estimators, and we just tried few of them, and we actually got better results. We plug in different estimators. So after we show that you can look on current methods, SSL methods, as information maximization problems, you can use different information estimators and just try them. It's very simple. And this is what we did, and we got better results. And also now I will talk a bit about generalization. Okay, so generalization is it's a big problem because originally the information bottleneck and all these information theory frameworks assume that you have all the probabilities and all the distributions, and you have everything. You just need to play with them, and you don't need to estimate them. And of course, in practice, it's not the case. We want to get models that will give us better generalization. Okay, so in order to prove some generalization bounds on these in these frameworks, we split the loss of these methods to two different methods. One is the regular loss, the regular SSL loss that we saw before. Okay, and the other one is, again, it's the same trick. So we will assume that we have labels, okay, and we will try to calculate this. We will calculate a loss with these labels, but in practice we don't have them. But let's try to bound it with other terms, even if we don't have it in practice. Yeah, I don't have time to go into the details. You can look on the paper if it's interesting to you. But basically, we bounded the generalization of these models with the regular loss plus some terms of the complexity. So here are it's the Radmacher complexity, and the most interesting thing that at least for me in this bound is actually that you can split it for the information that's relevant and the information that it's not relevant. And basically this bound replace all the examples, all the supervised examples that we have in the supervised case, it replaced them with examples with self-supervised, examples that you don't have labeled. So it means that when you have more and more examples, even when they are not labeled, they still improve your bound. And this is what we actually see in practice, right? We see that as we have in these models more and more labels, more and more examples, even though they don't have labels, the models improve significantly. Okay. Okay. Now I want to talk really briefly about, let's say, more applicative use cases, or what we can do with this information theory perspective. So one thing that we can do is to use it in transfer learning. So most of the time, you have in transfer learning, you learn a model with a lot of unlabeled data in a self-supervised with a self-supervised method, and then you have small number of labels for other data set, and you try to do a transfer learning. Okay, you're using it as some initialization. So if you look it from the loss perspective, so when you want to find an optimal solution, now you have labels, it's a supervised case, okay? And you want to find an optimal solution. So you start with some random initialization. X-axis is the parameters. And you start random initialization and you try to go till you find the minimum. What is the problem? The problem is that there is a difference between the training and the testing. And the difference between the two, we call it generalization gap. And in self-supervised or in pre-trained initialization, we assume that if we will learn something from a lot of labels, from a lot of samples without labels, we will have, and then we will use this point as a good initialization. We can transfer a lot of the knowledge and we will have a better guess, and we will go to a better place in the parameter space. Okay, this is what pre-trained methods are doing. Now, what we suggested is actually to use all the knowledge that we have already and to use the information that we have in our model, not only at initialization, but during all the training process. So what we want to do is to change the loss. We want to change the entire loss, and then we want to use it, as I said, to use it to change the loss and to hope that we will have better results. Okay, so this is exactly what we did. Again, I will not get into the details, but we have three steps. The first one, we learn a prior on the pre-trained task. Then we use the information that we have from the prior we use it as a regularizer. And the third step, we will do some inference. It can be Bayesian inference, it can be deterministic, but we use the information that we have, that our model got from the self-supervised, and use it for the transfer learning. The important thing, or why it works actually, is because we have some alignment between the pre-training and the downstream task. And we try to look on these alignments. Again, don't have time, but we look on different tasks, semantic segmentation, image classification, out of distribution, calibration tasks, and we found that we will have better results. I have 2 minutes or 3 minutes, and I want to talk briefly about a really nice thing that we did recently. And here again, we try to look on self-supervised learning, and we try to ask, what is the optimal representation in self-supervised learning? Or how the optimal representation, how the learn representation related to semantic labels, semantic classes. And the main question again is, what are the classes that the model learns? So just if you don't know, so in supervised case, when you have labels, there is something that's called neural collapse, and basically it's collapse of the representation to be the same for all the samples in each label. Okay, the variance of the representation goes to, for each label, goes to 0. And many people saw it in different cases with different networks and etc. But what we actually found, and again, I don't have time, but I will just want to give you intuition. So what we actually found, so we found something very similar that happening in self-supervised case. And in a self-supervised case, so remember, we have samples. We have, for example, one sample, one image, different samples, different augmentations of the same image, and we want to classify it. All these samples will classify to the same representation, or close to the same representation. Okay, so here the different colors. So each color is a different sample, and the points for each color is different augmentations for a given image. Okay, and this is the representation, like projection of the representation for the before the learning at initialization time. And now what we actually see, that after the self-supervised learning, basically all the samples, each image separate to its own representation. And of course, it doesn't surprising, because this is how we train the network, right? We train the network to separate between the samples. But what if we are doing this thing, this clustering, not with respect to each image, but with respect to the semantic labels, cat and dogs or stuff like this? So we actually see, again, really good clustering. So even though the network, we didn't present any labels during the training, the network knows how to separate them. And this process separates the classes, the semantic classes, really good. Okay, and this is what we try to investigate. And you can look also on some subclasses if you want, other subclasses, superclasses that you have, not dogs versus cats. You have animals versus I don't know, trains or stuff like more higher level. And here you also have very good clustering. And we investigate this and we looked on how these clustering emerged during the training process. Okay, when when it's happening, and also we looked on the information, and basically we saw also these two distinctive phases of compression and fitting. And the compression, actually, again, the compression phase, this is what bring you to clustering. And we look over the layers and different types of classes and random labels, etc., etc. Yeah, that's it. The final thing that I just want to briefly mention, that you actually can use it also for the supervised case. So we got the intuition from the self-supervised case. What does it mean to regularize using information, to regularize the network using information? And we can take this intuition and we can apply it again to the supervised case, and to give you a very good regularizer that actually bring you much better results in transfer learning and different tasks. That's it. We also have some projects about information in LLMs, in large language models, and their dynamics and how they evolve during the learning process, how the information evolves. You have very interesting phase transitions there. You can also apply it to hierarchical video representation learning. You can compress the information and you can control the information. That's it. I want to say thank you again to all the people that worked with me on these projects, students, collaborators, and mentors. Thank you.
Questions for Ravi? Yeah. So in your so-called self-supervised learning, you have already told the algorithm which images belong together in some sense.
Yes. So yeah.
What do you mean by it is finding these semantic relationships? It's already been told which images belong together. What I'm missing something fundamental here.
So okay, so in the last project, so the network trained on that an image, okay, of a dog and a different version of this image are supposed to be close to each other, but it didn't train the two different dogs supposed to be close to each other, or that dog and the cat versus the train supposed to be close to each other. This was like, again, the network, we didn't present any labels. We just present like that you have an image. It doesn't matter which image is it, but you have two versions of the same image, okay? And can be also masking, that you're doing just masking of the image. It's not even, it doesn't need to be even like augmentation. So it was surprising in this sense that the clustering is based on the labels, even though we didn't present them during the training. Is it clear?
So are we simply finding out that some measure of similarity in these, that's determined by this algorithm in these images, somehow it is consistent with our impression?
Yes, exactly. Yes.
Cats are more similar to each other than a cat is to a train.
Right. Yes. Exactly. So we don't have. I don't have the answer of why this is happening. We just pointing out that this is happening, and like you try to analyze different classes and different randomnesses and different difficulties, like difficult levels and stuff like this. But I don't have the answer why this is. It's a very good question, but I don't have the answer.
So I'll be then also to James. I was reading your review paper, really inspired by this idea of self-supervised learning, because as you mentioned, it allows you to use the data that you have in more ways to learn patterns. So as one example, James, you take a word out of a sentence, then you try to learn what word should be filled in, and then you do that interchangeably. And in that way, you decrease this problem of never having enough labeled data to learn by just creating the labels by masking, as you mentioned, from your data set yourself. And I thought that's what I would like to hear your opinion about. Like when we do Earth system modeling or environmental system modeling, we usually do it down a causal pathway. We use rainfall data to predict runoff, and that's all we do. And so we always have this problem of a high-dimensional system predicting a few target variables of interest. So we always face this problem of limited data.
Mm-hmm.
So my idea and suggestion would be if we would approach environmental system modeling as a task of self-supervised learning to, forget about the causal pathway for a minute and just have all the observables taken out at a time, learn about that and learn a single model to infill the gaps that we introduce, we would probably learn much more about the workings of this environmental system as compared to just always putting in rainfall, predicting discharge. So I'm actually quite excited about self-supervised learning and applying that to the systems that we have if we want to build truly integrated systems.
Yeah, so I'm a big fan of self-supervised, exactly because I think the most important thing in self-supervised, at least from information perspective, theoretic perspective, is that actually the noise helps you here, because as you have more versions of the same image or the same sample, if you have more perspective on this sample, your model basically can understand the important, the relevant, and the irrelevant information. This is exactly what a self-supervised is doing. So here you have two versions of the same sample, and if you assume that the shared information is the relevant information, then then all the other things are not important. And as you have more and more samples, even if they are not labeled, if you have more and more samples of the same thing, more versions of the same thing, your model will learn more and more. And this is why actually we want a noisier, or like at least not very clean data. And even if you have some noise in your data, you just need more and more versions, and you will be fine, and you will be okay. Your model will be okay because you know how to clean it. Your model learns how to filter the noise. So I think just put it in high dimensional space, give it as many as you can versions of the data, and you will be fine.
Any other questions? Yes, Holger.
No, that was for basic understanding relates to the previous lesson. Now, what I understood, so you're giving the system a series of pictures of a dog, and you tell them they all belong together. You give them a series of different pictures of a cat, and you tell them they belong together. You do the same with trains and with bikes. And in the end, your algorithm can group it into, so that the algorithm then groups cats and dogs together, and bikes and trains together, right? That's what it's like.
For example, you have a picture of a duck, and you have a black and white. So these are the same picture. So it's not the series of ducks. Still the same picture.
Yeah, okay.
Or a picture from the left and from the right. Then what happens to the overall cluster of all ducks comes. And we already mentioned it. This also happens at much more diffuse if you just mask out parts of the picture and have to reconstruct. Then you also get clusters. But these clusters, maybe you can correct me here. They're usually much more diffuse just with masking.
David?
Sorry, I didn't hear the.
Yeah, I tend to be quite silent, sorry. Yeah, I think I try to describe what you do in terms of use. So you can generate use from the same picture. Then you say they belong together, so that is the similarity score. Can you still hear me?
Mm-hmm. Yeah.
And then what happens is that you get clusters of all ducks and catchings. I think you mentioned it also. This even happens if you just mask parts of the picture out.
Mm-hmm.
So you also get clusters. I think you mentioned something like that. Like the style mask out encoders, you will also have this. But from what I know, they are much more diffuse than if you have a view-based way. View-based way tend to be much more diffuse than the label-based. So,
Much more what? Sorry. Yeah, much more what?
Diffuse. So clusters are not as nice.
Yeah, yeah.
And for self-supervised, they're not as nice as if you do have labels.
Yeah, that's true. So yeah, you're right. Like, so we looked on again in neural collapsing. So people looked on neural collapsing in the supervised case, and so the clustering there is really clear and basically like you will end up with just like without regularization, you will end up with just like one point for each class. And here it's much more like, again, you don't have labels and it's much more there are like some areas that you have like overlap between the classes and between the groups, and it depends on exactly on the exact labels, right? Because you can have a lot of different semantic labels for the same image and for the same data set. And so we try to look on it again, we try to look on it, we try to define like how can we what is the different types of labels that we can get, semantic label that we can get. And for example, you can think of different hierarchies that you have, and then like you can look on the overlap in different hierarchy levels and stuff like this. But again, I agree like that it's much more complicated.
Thank you, Ravid. Let's